Imagine to be in a theater, with the audience and a director of a grand orchestra, with a different instrument and distant musician, in one single perfect harmony. This is our vision of digital orchestration, where our instruments are not violins or wind instruments, but intelligent services.
And just as an orchestra relies on timing, balance, and coordination, these services can perform in harmony only when they are deployed in the right location across the network and are supported by the appropriate resources. Unfortunately, achieving this harmony is not always easy, especially given the growing number of next-generation applications that networks are expected to support.
All these applications require a large amount of resources, from the bandwidth between the microservices to the computational power that each microservices need to the computation of real-time process.
The Stream Pilot project was born to face this challenge, intelligently optimizing the network and the computing resources, minimizing the cost and the latency. And our final goal, to orchestrate next-generation applications to build more efficient, fluid, and increasingly connected digital future.
This proof of concept was designed within the SUPER project, one of the key initiatives of Restart, the largest national program in telecommunication, founded by PNRR.
The art of the demonstration, we have three key components. The first one is a video streaming platform developed by Mitico. Then we have the IDAGO algorithm designed by the University of Naples Federico II, which performs smart orchestration and resource optimization. Finally, we have the SUPER Orchestrator developed by Networks, which supervises the entire life cycle of services across the network.
The Mitico application consists of a video streaming platform that enables real-time processing thanks to AI models. Video streams coming from different devices, like cameras and IoT, are securely transmitted via WebRTC to the video room.
To balance the load, a broker node will make a distribution tree for each session, involving a video room and one or more AI tasks. The video room will then convert the received WebRTC stream to RTP stream to feed it into various AI task nodes also selected by the broker node. The AI task will perform the required processing and send them to the designated endpoints, while also updating their status to the etcd clusters.
IDAGO is our optimization algorithm. It's an advanced algorithm that is able to optimize how and when to deliver the service within the network. Its operations are based on two fundamental elements: the application description that is formalized through a service graph, and the network description that is formalized through a network graph. Based on these two information, IDAGO is able to optimize where to place a service function, how to route data flow, and how many network resources to allocate.
Behind the proof of concept lies the powerful infrastructure hosted on the premises of the University of Catania. It runs across three interconnected servers, one core node and two edge nodes, each with its own virtual machine, forming a distributed yet tightly coordinated environment. At every node, REC-EXEC modules oversee services, dynamically managing the resource allocation according to the current network conditions. According to this logic, the application's Helm charts are automatically deployed across nodes, guided by IDAGO, which continuously decides where each component should run.
To integrate it, a new resource allocation module was developed within the SOCR component. The module acts as a central coordinator for variable placement decision.
The resource allocation module gathers all the key computing and network information coming from different sites.
Once it receives detailed information about the infrastructure and application, IDAGO auto-generates the JSON data that define both the service graph and the network graph. Using these two graphs, the algorithm then computes the optimal orchestration solution to find the most efficient placement and interconnection of service component across the available resources.
Then IDAGO returns its plan to the module, which passes it to the service LCM component, the part of application responsible for launching the services. Finally, service LCM component deploys everything running through the local REC-EXEC at each site. All these modules are running smoothly as Docker containers inside Kubernetes clusters.
The integration of the IDAGO algorithm into the SUPER Orchestrator brings significant advantages compared to the basic techniques: reduced deployment costs, lower latency, and above all, smart resource allocation, driven by innovative algorithms. We have demonstrated how advanced research solutions can be successfully applied in real-world contexts, concretely improving the efficiency of orchestration systems.
The introduction of the multi-layer, multi-domain super orchestrator, enhanced by innovative algorithms such as IDAGO, opens the door to advanced network optimization capabilities that will support next-generation services and applications. For this reason, SUPER, the structured project within the European-funded Restart program, which includes key industrial partners such as TEAM, initiated the development of a proof of concept based on Oral Alliance Service Management and Orchestration Function, the SMO platform for RAN management, specifically centered on these technologies. The SMO platform by TEAM was further enriched by the contribution of the 5G Academy students, who translated the initial ideas into a concrete and compelling demonstration.
With this proof of concept, we want to demonstrate something that goes beyond technology, our vision. Intelligent and programmable networks capable of orchestrating complex systems efficiently, reducing cost and consumption. Because technology and innovation can and must work together to build the future greener and safer.